Welcome back to Practical PyTorch. A slow model is usually not slow where you think. Often the GPU sits idle, waiting for data. Let's profile a real model and find the one thing that is actually slow. Your guess about what is slow is usually wrong. In a beginner's training loop, the GPU is often idle. It sits waiting for the next batch, not working. Guessing at a slow model wastes hours. A profiler shows you where the time goes. It shows the operations that ran and where the GPU did nothing at all. This video has 3 parts. First, the profiler table. Self-CPU versus self-CUDA time, that is where the work is. Second, the trace timeline. A gap in the timeline means the GPU is waiting. Third, Dataloader-Bound versus Kernel-Bound. We raise num workers, then remeasure on the same axes. Part 1. The profiler table where the GPU time goes. Torch.profiler records every operation inside a block of code. We open the profiler with a with block and call it prof. We ask it to watch both CPU and CUDA activity. Inside, we run a handful of ResNet 18 training steps. This is a real model, not the tiny toy from before. A toy is too cheap to ever bottleneck. Each batch of images moves to the GPU. We run the forward pass and compute the loss. Then backward the optimizer step and zero the gradients. After the block, we print key averages as a table, sorted by self-CUDA time. Each row is one operation. We sorted by self-CUDA to rank the GPU work. Aughton convolution backward is widest, at 37% of the GPU time. Then batch norm backward, the forward convolution, a layout kernel and ray-LU. Now drop to the footer totals. The self-CPU total is about 6.4 seconds. The self-CUDA total is only 784 milliseconds. The CPU is doing far more wall clock work. A first hint the step is host-bound. So the ranking tells you where the GPU spends its time. The totals hint the step is host-bound, but the ranking still cannot find the idle gaps. For that, we need the timeline. A table's ranking shows only the operations that ran. It cannot see the time when nothing ran. The totals hinted host-bound, but not where the idle time falls. 2 runs can share the identical ranking, yet differ hugely in speed. One wastes its time between the bars, waiting. Only the timeline shows exactly where the gaps are. Part 2. The trace timeline where the gaps are. This is a schematic of what any training step trace looks like. The real ResNet 18 ops are the ones in the table. The top lane is CPU work, loading and preparing each batch. The bottom lane is the GPU, running kernels. These named blocks are the GPU operations. The names here are generic stand-ins, not ResNet 18's exact trace. Now look at the wide empty spaces between the blocks. 2 lanes, 1 time axis, and the GPU blocks are small and far apart. The schematic rings the widest GPU block. It stands for Aughton convolution backward, the table's top op. The urge is to make this 1 bar faster. But keep your eye on the whole lane. The bars are only a small part of it. Look between the blocks. This wide empty stretch is the GPU doing nothing. Another gap sits here. The GPU is waiting for the CPU to hand it the next batch. These gaps are wider than the kernels. The GPU is idle most of the timeline. This is the real problem, not the widest bar. Put a number on it. At numWorkers 0, the GPU is busy only 11.5% of the timeline. The step takes 691 milliseconds. This busy fraction is derived. It is busy kernel time divided by wall clock, read off the trace. It is not a cell in the table, so don't hunt for it there. 11.5% busy means idle about 88% of the time. The GPU is starved, and a faster kernel would not close one gap. Part 3. Dataloader-Bound versus Kernel-Bound. The gaps are CPU work, decoding and augmenting each image, so we rebuild the data loader. Same train set, same batch size of 64. Now numWorkers is 4. 4 processes decode and augment batches in parallel. Pin memory is true, for a faster copy from the host to the GPU. The model and its kernels are untouched, only the feeding changes. Same run, now numWorkers 4. The gaps have collapsed to hairlines. This gap closed too. The GPU blocks now packed tightly together. The kernels are the same size as before, but batches arrive sooner, so the GPU is fed far better. This schematic overstates it. The real gain comes next. Remeasure on the same axes. GPU busy rises from 11.5% to 44%. The step drops from 691 to 187 milliseconds, 3.7 times faster. Now look at the self-CUDA total, 784 versus 812 milliseconds. The GPU did the same work either way. Only the feeding changed, so this run is Dataloader-Bound. Be honest, 44% is better, not saturated. The real win is the 3.7 times speedup. The same story as a bar chart. Panel A is GPU busy, 12% at numWorkers 0, rising to 44% at 4. Panel B is step time, 691 milliseconds, falling to 187. Same kernels, better feeding, the before and after of a Dataloader-Bound fix. Measure, fix, then remeasure. The reflex is common. Open the profiler, find the biggest kernel, and try to make it faster. But on a Dataloader-Bound run, a faster kernel closes 0 gaps. The GPU was already idle, waiting. Optimizing ONT convolution backward here does nothing. Only the trace tells the two cases apart. A packed lane with a dominant bar is kernel-bound, fix the bar. Wide gaps are Dataloader-Bound, fix the feeding. Widest bar and widest gap are different diseases. Measure first. Torch.Profiler gives a table, self-CPU versus self-CUDA time, and a trace timeline. The table shows the bars. The trace shows the gaps. A gap is the GPU idle, waiting for data. Find the widest bar, that is kernel-bound, or the widest gap, that is Dataloader-Bound. Then fix that one thing. Here, raising numWorkers cut the step 3.7 times with the kernels unchanged. Then remeasure. 1 to try. The trace shows the GPU busy only about 12% of the timeline. It is idle most of it, with wide gaps between kernels. Do you shrink the model or raise numWorkers? Raise numWorkers. The run is Dataloader-Bound, so a smaller or faster model won't close a single gap. The reasoning is in the answers file, section 3.5. Next, we read the most feared PyTorch error, CUDA out of memory. We find the 4 things actually filling the card.